So before I start my talk, let me recall that robustness is the ability of an AI model to be resistant against a bunch of perturbations. So we started working on this topic since the beginning of the program. And now I will tell you a bit about what we have done this year. So I will suppose that you know everything about what we did during the first year. So that's, of course, a joke. So here in this, on the screen, we can see how our activities were organized. Mainly, they were split into 4 main blocks. So first of all, we worked on empirical methods of robustness. So empirical here means that these methods perform well in practice, but we don't have formal or mathematical proofs why they do so. And in this category, motivated by, of course, by the industrial challenges that are available in the program, we launched activities on conformal predictions for time series, Bayesian neural networks, continuous time neural networks, and this year we integrated activities on symbolic AI in partnership with our startup partner, My Data Models. So this is an important step towards considering hybrid AI. Today there is an agreement that hybrid AI should be the right path to reach trustworthiness, and this is among the goals of this program. So the second block is about exact methods. So the advantage of these methods is that they have provable and certifiable properties, despite the fact that in practice they perform less better than empirical methods. And in this category, based on our works during the first batch, we launched activities on Lipschitz networks. So this activity is more related to the design phase because Lipschitz networks are robust by design architectures. We use them during training. And we also launched activities for posterior evaluation. And this consists on the improvement and the maturation of the PIRA tool for formal verification. So this tool was proposed and initially developed by SEWA, and since the beginning of the program, we are improving it. The third block of activities is related to environmental alterations. So we pursued our works on adversarial attacks, and by this year we enriched our, let's say, adversarial attacks library with new state-of-the-art attacks. And also we launched new types of attacks, like patch attacks in the case of classification and also detection, as well as watermarking attacks. Now, finally, the fourth block, which describes our activity, is about visualization. So we devoted a large part of our work to visualization. And so first of all, we relied on a tool by our startup partner, Kereval, which is Kiru. So this tool is now used in the project to display different kinds of metrics and graphics related to evaluation and analysis of performances, etc. As well as a tool which is called DeepAI. So this tool was first introduced or developed in the project EC5. So it was presented in the previous slides also by Florent and Angélique. So we borrowed this tool and adapted it to display scores related to performance, to analysis of performances. Of course, these blocks have a lot of synergy. For instance, empirical methods give valuable informations for exact methods, because in some sense, the performance of empirical methods is the limit or the upper bound for the exact methods. We can also, for instance, use feedbacks from the environment alterations block in order to improve training by empirical methods and also exact methods. So now, in the rest of the presentation, I will show you some illustrations and give some details on the techniques that are displayed here. So first of all, regarding the study of iterations, before going, let me go back here and say some words about the covering in terms of use cases. So we were able to illustrate the utility of these techniques on 2 use cases by Air Liquide, as well as the use case by Renault, which is the Renault welding use case, as well as now we are actually working on applying these techniques on a use case proposed by Safran. So regarding environmental alterations, here you can see on the picture on the left one typical example of adversarial attack on the Renault welding use case. So I recall that the goal or the main problem for this use case is to predict whether welding has been done correctly or not. And here what we did, of course, we generated a bunch of attacks on the models that were designed on this use case, and then these samples were used to improve training. We also carried out studies on the magnitudes of attacks, let's say the minimal magnitude that is needed to fool the AI models. And on the right, you see another type of attacks, which is patch attacks. So the goal here is to add some foreign object on the image in order to fool the system. And we made a similar study on the minimal size of this object in order to succeed in fooling the system. So the second, we also applied techniques to prevent watermarking attacks, and illustrated this on the Renault welding use case. So watermarking attacks attempt to replace the model that is tested or deployed by another one. So we developed techniques that are able to prevent this type of attacks. So next, let me say some words about empirical methods. So in this block, we considered let's say the 2 domain of applications, time series and images. So first of all, we were motivated by a use case by Air Liquide on demand forecasting. So the goal here is that in this use case by Air Liquide, which is where we get informations about historical informations about the demands of customers in terms of gas quantity. So for Air Liquide, it is more important to predict intervals of the demands instead of exact values. So this is due to the fact that there is a lot of variation between different persons, and also for the same person through different years. So we were able to apply conformal prediction techniques on this use case. And here, for instance, on the right, you can see in blue small segments that contain the true prediction of the gas demand. Also, we worked on Bayesian neural networks for the same goal to predict intervals instead of an individual, let's say, predictions. Using Bayesian neural networks. So this architecture is different from usual, say, classical neural networks in the sense that here the weights of the network follow some distribution, and so the final output also follows some distribution. And from this final distribution, we extract the intervals that correspond to confidence intervals. Also, we launched works on continuous time neural networks. So basically, neural ODEs and diffusion models. So in few words, so neural ODEs. So these are architectures where layers are indexed by time, and these architectures are robust by design, and they were also applied to different use cases on images and also time series. So as I said at the beginning, so this year we launched some works on symbolic AI in collaboration with my data models, and now we are currently applying it to the use case and understanding by value. Now let me say few words about exact methods. So first of all, we made important improvements of the DEAL Leap. So this is a library initially developed in the DEAL project to train Lipschitz networks, and it is available in open access, and we also applied it to several use cases. For instance, the one by Renault and also Airbus. And here you can see some metrics related to the improvement of the PIRA tool also that was proposed initially by CA. And to end this presentation by some visualizations, so here on the right we show some visualization from the DeepAI tool. So using this tool, this year we were able to display many metrics of models that we trained and that we designed during the first year. There is one demonstration about DeepAI in the village, as well as one demonstration on conformal predictions, and 3 posters on topics here in my presentations. Thank you very much.